Sciences from this very university where you're sitting today. He was the initial developer of Linux operating system and has also worked in public key cryptography and one of the developers of PGPI, the international version of PGP. He was a scientist at National Aerospace Laboratories in Bangalore from 87 to 91, where he was one of the key people who designed and prototyped Hansa, India's first indigenous aircraft for flying training. He was invited here at Delft, where under esteemed emeritus Professor Egbert Turnbrink in 1989. Here he was an employee at two departments, aerospace engineering, computer sciences. Today he's settled in the north of Italy, where he founded and runs NASHERO. I think some part of that he will talk about, probably not a lot of it. Welcome again, Dr. Sharma. I'll bring up the slides up.
So this one is going to be an interactive session. How many of you actually are from aerospace engineering? Can you raise your hands? There's no one.
Mechanical at least.
So I'm actually going to cover my background over here, and this is about designing aircraft across generations. I've been making tiny airplanes since I was 3 years old. So I'll go through this. Basically, the idea is to inspire the young folks who want to do something which has been burning desire in their depths of their hearts, and to inspire you to go ahead and do that. In spite of the difficulties, making an airplane is not a simple job. There are a lot of disciplines involved in that. And as you'll see that we have done that. So I'll start with incubation, and I'll quickly run through the slides, and then I'll invite questions from you folks. So the first I'll talk about this incubation. The first aircraft, Hansa, which was my master's thesis at IIT Kanpur. And now there are a number of aircraft that our company is making. We are also AS9100D certified company. EASA certifications we have, which are things which very large companies have, and we are a smaller company than that. So this is something. I used to make airplanes like this when I was 3 years old. Okay, this is from my school times. Another is something from my school times. And this is a little recap. I used to be the IIT Kanpur Sumitian captain. And I'm sorry, Vikram, that is from Tal Katora. We smashed the living daylights out of IIT Delhi. and that's me holding their model. This is also, I don't know if any one of you, there are people from IIT Kanpur. So in IIT Kanpur, we have a TA102 lab. And in that TA102, I designed that engine and I made it. And this is that engine function. This is, I was a mechanical engineering student, not an aerospace engineering student. And I did this as my final year BTech project, in which Saurav was my project mate over here. So, and this is me flying gliders in 1996. I was a flight instructor. I still am. This is the airplane that I designed. So what happened was that in 1985, I gave a presentation at the Aeronautical Society of India's annual general meeting in Calcutta. And somewhere in the front of that was Professor Rodam Narasimha, who later on became the director of NAL. Actually, he was the director of NAL at that time. And Professor Rodam Narasimha said to me, come and visit me in my lab. And I went there, and he said, you can do whatever you want. So I said, I want to design a glider. He said, no. In India, gliders are rich man's luxury. So what you can do is something that is useful. So we decided on making a plane, and this started out from scratch. Professor Thornwick heard about it, and he invited me to come over here in that. So now we come to, after a long career as an entrepreneur, as a chief executive of large companies. I ran a company in Netherlands which was 2,500 employees, and that still exists, so I didn't do something bad. And it has grown. And being a venture capitalist in a fund here in Netherlands, and then it was called Nespec. Unfortunately, that fund is no longer there, but people of that fund are around here. And I eventually settled in Italy. And this is the first aircraft that came in my mind, because I wanted to design, build, and fly my own airplane around the world. This is extremely good aerodynamically, very clean. And if you look at it, why Augusta? If you compare the range versus cost of the current breed of airplanes, which are exactly like, so this is the current breed of airplanes, okay, which is listed over here, which have exactly the same maximum weight and exactly the same engine as the one that we're using. And look where we are, and we're there. So this is thanks to some composite technology that we have developed. I actually teach at Stanford University composite materials nowadays, and work with Professor Stephen Tsai. So that is thanks to this weight advantage that we have that we get that. Then there are about 75 patent pending technologies that we have, and that gives us, if you divide speed performance by cost versus a consolidated safety index, then the rest of the bunch of planes are here, and we are there. And these are non-dimensionalized numbers. That's the reason why we have this aircraft. I started out in an industrial facility in 2000 November, started doing all these things by myself. This is a machine that I designed, and I got it crowdsourced. A company in China made the machine for us, and they sent it to us. And these are my friends. These are two of these are my students as pilots, and they came to help me set up the machine. This is making the fuselage, the master of the fuselage of the aircraft. This is the quality. You see, this is the reflection of the ceiling of our facility on the wing. This is again the machine at the back. And this is this was taken by DMG Mori, company from whom we have purchased machines, because they couldn't believe that this reflection that you see of the windows, it is so high end that none of the car manufacturers like Koenigsegg or Bugatti or Pagani, I don't know if you know these names. These are the highest end car manufacturers in the world today. Their cars cost about $7 million. And none of them have this quality of the part. So I started out with I showed you the master model. From the master model we make molds, and from the molds you get this quality of aircraft. You get this quality, and this is a door panel of ours. Of the aircraft. This is a photograph from 2013, and this is the reflection of the sky over here. So basically, at that level, you do not check the quality of a part by any other means other than visual reflection, because that's the highest level of your eyes have the highest level of precision over parts. These are some parts made, look at the weight. The thing that we're talking about is 433 grams, and this guy can take over 800 kilograms of shock. So these are some of the parts that go in the aircraft that we have, and this is structure tunnel inside the And these are all parts which have multiple patents on them. This is the actual aircraft. And I haven't brought an image of the actual aircraft because it is under assembly and it looked terrible. So you won't understand what is where. This is the actual aircraft that has been designed. And now the company itself is AS9100B certified. We are a NATO supplier. We have this certification code. We are design organization approval, type certificate is in progress, and we have a production organization approval. And the scope of this AS9100D, if you compare with the AS9100D that Tata Aerospace Systems, for instance, has, it doesn't have this extensive scope that we have. So the devil is in the details, and we have actually done the one aircraft which has gone through the entire design to production complete, production cycle. The design of four other aircraft types is underway, and we're doing those. And we have a production facility planned in 2024 in which the Italian government is interested in investing in about $40 million because we're not making a software company, we're making real bricks and mortar lookings and feelings, so we say. So this is where we are putting it. Now this is something about I have an interest in doing things for the country, and this was one of the panel discussions that I was invited to. This is Professor Sai, who is a 94-year-old guy, is considered to be the father of modern composite materials, with whom I have written 3 books, and these are those 3 books. This was written at ICM and ICCM International Conference on Composite Materials 2-3 months back, and that's the 3rd book that you see over there, second and the first one, and the second one is being presented at JEC World in Paris last year. And this is a bunch of IIT students who came to the ICCM 2 months back in Belfast, and they grabbed me and wanted to have photographs. So this is IIT PhD students. And this is, I'm a flight instructor, so I fly sailplanes and instruct at anything. So this is basically a short and a quick review of the scope of what I do. So if anybody has questions, I'm very, very happy to answer. Yes?
So, as I understand correctly, you're still working on combustion-based technology?
Yes.
Do you have any plans for the Ford in that future after the war?
No.
No.
No. And I'll tell you why. The lithium-ion systems, if they burn it for 2,000 degrees centigrade. In aircraft, we have firewalls to prevent the fire from coming from the engine compartment or the storage or thrust converter into the cabin. There is no material today available that will handle 2,000 degrees centigrade. Our current firewalls handle 1,115 degrees centigrade. The same thing is with hydrogen. Hydrogen and lithium systems, despite the fact that their specific energy density is down in the dumps, they do not require air for that ignition. Okay, so that's the reason. And people say that we will have. The reason why they have a burnout is because there's a fast draining of the energy or fast charging of the energy in the system. But that's not the only reason. Dendrites will form and they are random process. So there is no way you will know that there is an imminent explosion that is about to happen. Many aircraft which are today under development using that process, they underuse the ability of the thing. The same thing with hydrogen goes up to 3,000 degrees centigrade. Yes, please. Right.
slide. Does it have any application towards adaptive stealth technology?
Stealth?
Yeah.
No, the reflectivity is, so basically stealth has a different issue. You know, stealth, the reflectivity of stealth comes from metal embedded inside your aircraft, which reflects the radio, okay? Reflects radio waves. Radar signatures come from the reflected radio waves. The high surface finish that we have is for extremely high natural laminar flow capability of the aircraft, which reduces significantly the drag of the plane. Yes?
You talked about the weight, the part 840 program that you took.
Yeah.
And then you also talked about the car manufacturers not being able to do something similar. So most of them use carbon fiber as a composite material in order to make it lighter. So I know that carbon fiber is not that strong in terms of taking stress. I believe so.
No. Carbon fiber is extremely strong.
Okay.
1.2 gigapascals. Carbon fiber can take 1.2 gigapascals. Show me one metal that can do that unless it is like titanium.
I see. So the question is, so how do you compare this material to carbon fiber in comparison with the automobile industry in terms of body, etc.? Because that's what they finally use.
Yeah, it's a good question. The thing is that we use carbon composites because that is the ultimate level of material that you can use that gives you the highest strength, specific strength. That means strength divided by the mass of the weight. And we have a technology that is developed with Stanford. I teach at Stanford, I mentioned that. So we have a technology developed with Stanford that's called double-double, on which you saw those 3 books written. That has the capability of reducing the structural mass of aircraft by 55%. That's the reason we use it in aircraft. In automobiles, such fine reduction of mass is not necessary. So that's one reason. The other reason is extremely expensive to make things using that. Means Lamborghini has a project in which they have chopped strand materials which are a waste of our process, and they compact them under heat and pressure and inject a thermoplastic resin inside. And that can be done in volume, but not at the volume that car manufacturers want.
Just one question. First of all, congratulations on a lot of great work done.
Thank
Very
you.
proud of you.
Thank you.
See, compared to lithium, I would like to know where you're targeting your, what is the target market for?
Let me just point out, he just mentioned the name of my competitor.
Okay, so you accept.
I will just make a comment about that because we have 5 aircraft in our pipeline, and one of them indeed is a competitor of lithium. Lithium and all the other breed of current eVTOLs, that is electric vertical takeoff and landing aircraft, the biggest problem with them is that they don't have any glidability. So if you have a problem while you're flying on a concrete jungle, and a concrete jungle is like Manhattan or Melbourne or Milan, and you have an incident, a small incident, 5 sparrows go inside it, and it sucks up because if a bird comes over here, these airplanes, it's packed with engines on the top, it sucks it up. Will get destroyed. It doesn't have any glidability to get out of that. So their failure scenario is that we will activate an emergency parachute recovery system. But how many of you will be happy to have an 11-ton brick land on your head if you're nicely having an evening promenade walk on the ground? I won't. That's the problem with that. And then the same thing with the power systems. They use lithium. Okay? And you know that on the ramp, this aircraft called Aviation's Alice, it just got incinerated. It was packed with lithium batteries. It was not doing anything. It was sitting on the ramp. And poof, it went off. Yeah.
Continue the questions in the coffee break.
We can continue the questions in the coffee break.
Thank you.
Sorry,